Hello, I am going to show you 5 types of molecular shapes. And now, why are there molecular shapes, and why don't I just show you the Lewis dot structures? That's because of a theory known as VSEPR, which states that the Lewis dot structures don't show you the shape, and the shape of the molecule determines what chemical components it has. Now, the first one we're going to be looking at is a linear shape, and the example we'll be using will be carbon dioxide, or CO2 if you want the formula for it. Now this one, and now for all of these molecules, the jelly beans here will represent electrons. The color signifies nothing. They are all electrons, and each of these gumdrops will represent a different element. Be warned that the same color gumdrop could be used for a different element in later diagrams, but the color signifies a certain element each diagram. And for this particular diagram, the yellow gumdrop represents carbon, while the 2 orange ones represent oxygen. Of course, you see the electrons there, and in the structure, there are 2 toothpicks, both linking them together. These are the bonds. As you can see here, both of these oxygen elements are combined with the carbon through a double bond. Of course, the symmetry is nonpolar, and this is important because that shows how it works magnetically. If an element is polar, then it works similar to a magnet, where it has a north and south pole, and each side will divide up. Nonpolar, on the other hand, it'll all balance out, giving no real charge on either side. And this element is nonpolar, and of course the bonds are separated via a 180-degree angle. Next is the bent structure, which we will be using sulfur dioxide, or SO2. Of course, this time the red-orange ones will signify oxygen, and the just plain orange one will represent sulfur. And in order to avoid confusion, this one right here is sulfur, while the 2 here are oxygen. And of course, each electron is there, and of course the bonds. There is 1 double bond here, 1 single bond here. A particular note for these kinds of bonds: it doesn't matter where you place the double bond, as long as it has it. Of course, the angle is at 104.5 degrees, and it is nonpolar. Next is a trigonal planar. The element we'll be using for this one will be aluminum trifluoride. Now, the green one will signify aluminum, while the 3 reds will signify fluoride, or yes, fluorine if you want to call it by its regular element name. Now this one, all the electrons are here balanced out. It has a polar symmetry, and of course the angles here are separated by 120 degrees, of course, and of course the 20-degree angle at the top. And now, I should also mention that each of these angles, it has one double bond and two single bonds, and also to note that this double bond can be anywhere on here as long as there is one. Now is the tetrahedral with carbon tetrahydride. This one is the green one will represent carbon, while the red ones will represent hydrogen. It doesn't have any outside electrons, and all of them are separated through bonds. And of course, each of those bonds are separated by 109.5 degrees. It also has a polar symmetry. And of course, each of the bonds are single. And the last bond that I have made a diagram of is a trigonal pyramidal, which I use nitrogen trihydride, or NH3. Now, this one has an electron structure on the base element, which like the bent one, does move the bonds a bit. Of course, this one earlier has the same idea. Now, and of course, for this one, the area over here is separated to 107 degrees. Along with, of course, the yellow one is symbolic of nitrogen, and the red ones are symbolic of hydrogen. This molecule has a polar symmetry, and that's it for that one. Now, these two I did not make models of, but they are worth mentioning. This one is a trigonal bipyramidal, and this is what it looks like. The one over here is a octahedral. I'm sorry for the quality blur there. And this is the model of it. And that is all of the models in there. And thank you for watching.